Hello, everyone. Welcome to Injection Molding, a solution for more than just production. I'm Carlos Gonzalez, Special Project Manager of Mechanical Engineering Magazine and ASME, and I will be your moderator for today's event. Before we get to the topic, let's get some simple housekeeping items out of the way first. The console you are looking at is completely customizable. From the presentation window to the Q&A panel, every window you currently see can be moved, enlarged, or collapsed, so if you want to change the look and feel of your console, go right ahead. We would like today's webinar to be as interactive as possible, so please feel free to post your questions and comments throughout the presentation. If you have a question for our speakers, please enter it into the Q&A widget. We will get to as many as we can during the live Q&A session at the end of the event, and if we don't, you may receive an email response from our speakers and the sponsoring company. For more information on this topic, you may be sure to check out the resource modules where you can download related materials. If you need to leave early for any reason, don't worry, the presentation will be recorded and available for on-demand viewing starting tomorrow. Now let's get to today's topic. Our presentation today comes from Fictive, a digital manufacturing ecosystem that rapidly delivers custom mechanical parts on demand through its quote-to-order platform and a global network of manufacturing partners to help engineering teams accelerate new product innovation. Fictive is free to use and can partner with you for all your injection molding needs. No minimum orderable quantities, free DFM feedback, and C1 samples as fast as 2 weeks. Today's presenters are Kyle Adams and Kinsey Mead. Kyle is the Senior Technical Solutions Engineer for Fictive. He has over 18 years of industry and experience in injection molding processes and works with companies across several disciplines, including medical devices, aerospace, defense, and automotive. Kinsey is a mechanical engineer with experience in product design and DFX for consumer electronics industry. At Fictive, she creates technical content to help other engineers up-level their understanding of key DFM and mechanical design principles. Today's webinar will explore the benefits of injection molding, how you can produce high-quality production-grade parts at prototype speeds for design validation cycles. Again, thank you for joining us today. Kyle and Kinsey, the floor is yours.
Great. Thanks so much for that introduction, Carlos. As Carlos mentioned, we'll be talking about all things injection molding, starting out with some of the benefits of plastic injection molding, and then talking about where injection molding fits into the product development process. We'll also touch on how to get high-quality parts and how to decrease your lead time, because we know everyone wants parts quickly and at the quality that you need, and then we'll finish up with some Q&A, so definitely make sure you're asking questions in that box. Let's start with a little poll. So in your design process, working with injection molded parts, when do you begin to engage with your tool maker? Do you start kind of during the concept phase, right at the beginning, when you begin prototyping, later during validation stages, or do you start right before production begins? We'll also make sure to fill out that poll. All right, so it's looking like, a lot of people like to do injection molding later in the process, maybe during production. It makes sense for large quantities of parts, but we're going to talk a little bit about doing it earlier in the process. So let's get started. First, as I said, we'll touch on some of the benefits of plastic injection molding. For one thing, it's a really cost-effective and quick turn process. Once you have your mold finished and ready to go, each part is made extremely quickly. Single cavity tools can produce as many as one part for 30 seconds on average, so you can get 500 to 1,000 parts per day, which is great when you're heavy into that production cycle. This allows the quick turnaround on part production orders to meet demand that you may have for your products. There's also reduced part scrap compared to other processes. You're not removing material other than maybe a little bit of material for the gates. So overall, all the material that you're using is going into the part itself. This contributes to a lower price per part compared to other processes, as does the time required to make each part. And so those things, especially when spread out over large quantities, result in a low average price per part. Injection molding is also an extremely accurate and precise process. You can get really repeatable, consistent parts once you nail down the process parameters for your mold and press. each part is going to come out exactly the same, and each of those parts can be held to really tight tolerances. 0.005 inch tolerance bands for regular injection molding, and as low as plus or minus 0.001 for precision molding. So this makes it really good for those precision applications like medical devices or aerospace, parts that need to be perfect every single time. Oh. Sorry, there's that slide. And then with injection molding, you have a really wide variety of material choices. We're talking about plastic injection molding today, and there are so many different resins that you can use, and they have a wide range of properties. So depending on your application, you can choose for strength or chemical resistance or electrical resistance, or you can do a blend of materials that will give you exactly what you need. Plastics themselves are very versatile. They're durable materials, resistant to contamination, and they're lightweight. So they have a wide range of applications.
All right, so what we want to do is we want to talk about the injection molding in the product development process. Give a couple of breakdowns on some different tooling options that you have. First, I want to start with just a real quick brief overview of the injection molding process. It all starts obviously with the tool design and build. Once that tool is complete, tool gets loaded into the press. Plastic is then injected into the tool and cools. Once that plastic cools, just enough to hold its shape, tool opens, part is ejected, the process repeats itself. There are a couple of other processes that are out there similar to injection mold, more so on the thermoset type material, which would be compression molding, transfer molding, or LSR. Again, these are all typically in the thermoset materials, more the softer rubber or silicone type molding. What we've got here is just a couple of different options to make your decision for which direction you want to go: prototype, bridge tool, design validation, whatever you're needing at the time. You can go down the path of cutting an aluminum mold, which will allow you to run a small amount of parts within certain limitations, but it's an option for a true prototype tool rather. The other option would be to go with maybe more of a sort of a steel mold, not traditional, but steel mold that will allow you to achieve your prototype tool type of requirements, but also can help bridge that gap and allow you to run production parts at the same time. Overall, as you see from the chart, lead times are very similar. There's not a whole lot of difference between those when it all comes down to it. The aluminum tool typically costs a little bit less, but there's a reason for that. One of the main reasons is that with the prototype tool, what you're getting is actually typically a core and a cavity insert that would fit into a larger frame. That frame is usually already installed on a press, so you're truly only getting two pieces of metal. Again, the reason that this costs a little bit less is because you're getting less. The other thing you'll notice there is the tool life, typically about 10,000 parts. You start seeing a little bit more wear than you would out of a traditional tool. There are a couple of fairly significant differences between aluminum and steel, obviously other than just the material. Unlike an aluminum prototype tool where you only get those core and cavity inserts I mentioned, typically when you go to that steel mold, you're getting more of a complete mold. It's the entire thing, as you can see from the image there. Tool life, obviously tool life's a much higher quantity versus the aluminum. You could get 50 to 100,000 parts out of the tool and then some. Again, depends on part geometry, material limitation, things like that. Production tool. This really is the luxury car. This is got all the bells and whistles. It allows you to run 24/7 operation, producing unlike the reference that Kenzie mentioned earlier, the 500 to 1,000 parts a day. With this, depends on the cavitation you select. You could get tens of thousands of parts a day. Again, depends on just how far you want to go with it. Tool life, obviously, well above that 100,000. Sometimes with these tools, you can get into the millions and millions of parts. It just depends on your requirements. Obviously, all that comes with a much higher cost, 25,000 or well in excess of that. There's often times where people are spending millions of dollars on molds just for one. All that comes with a much longer lead time, though, as you can see.
So Kyle, what are some reasons that someone might start with a design validation tool like you just talked about and then proceed with one of these high volume tools?
So obviously there's a tremendous cost that comes with this high volume tool. A lot of times investing in that cost without truly validating, make sure the design is what you're needing and wanting is critical. A lot of times what customers and people want to do is they'll want to use that design validation tool to work out any kinks, work out any bugs. You can spend a lot less money, still get a molded part, have some takeaways, your learning lessons on the part, make some engineering changes so that you can actually shorten that lead time that's noted there on that high volume tool. Manufacturing location, obviously there's lots of options, lots of countries that are manufacturing tools. What we want to do is kind of go with the two called big players between a U.S. aluminum tool and a steel tool that's made overseas in Asia. Again, there is some significant difference there, but put together a quick little hit list there for you to take a look at.
What would you say is the main difference in your experience between a U.S. tool and a tool from Asia?
Cost, when it all comes down to it, is very similar. There's usually not a significant difference. The biggest difference that I've found is just in the shipping time. Obviously, if you're located in the States and you buy a tool from a U.S. partner, a U.S. supplier, there's a lot less shipping time and shipping costs associated with that, as it's noted there. When you're sourcing something overseas, you have to factor that into it. But again, that comes with advantages and disadvantages at the same time.
Mm-hmm. I see one of the pros here is proximity of secondary shops. Why does that matter?
So obviously there's a large pool of manufacturing being done in regional centers within Asia. A lot of times what happens is you have these different secondary shops, whether it's texture shops, heat treating, material distribution, all very centrally located. You don't tend to find that here in the U.S. as much. So a lot of times you're having to ship that mold, not just across town, but really sometimes across the country to achieve that texture or achieve that heat treat. So you have some shipping back and forth, which of course that adds up with both time and money.
Awesome, makes sense.
Again, another little chart that kind of throws all the different options out there, allows you to see kind of a quick breakdown, comprehensive guide from all of our previous slides.
One thing we haven't talked about too much yet is the finishing options. Why is this more limited for an aluminum tool?
You're not able to polish aluminum like you can a steel tool. So a lot of times if you follow, which we do, the SPI standards, you're typically only able to achieve an SPI A3 polish on aluminum tools. So if you're needing something that's a high polish, you just can't quite get that with aluminum. Same thing with texture. If you need a textured part, after running parts, 10,000 parts, that texture starts to wear down. So your first part off that tool and your 5,000th part of that tool will actually look different just because of that wear. So again, you kind of have to stay within those finishing options.
The lead time also, we see a big jump from the rapid design steel mold, 2 to 4 weeks, to the 8+ weeks for production tooling. Where does that big increase come from?
Big part of that actually is in the design of the tool itself. A lot of times what you find is because the high volume production tool truly is custom, you've got sometimes 2 weeks just in the pure design stage. So in contrast, you go 2 weeks for the design, you go over to that rapid design steel, you can almost have a tool complete in that same time frame as just you're designing that production tool.
Gotcha. And then finally, tool life. We see a lot of variation there too. Where do some of the differences come from there?
Yeah, so I've mentioned wear. Again, what that means is as you're injecting that part 10,000 times, or that tool 10,000 times rather, you do start to see wear. You start to see maybe the parting lines start to slip a little bit. So you may start seeing more flash. You may start seeing, if you have slides or hand loads, depends on the type of tool that was made, you start seeing a little more wear on that. So then at that point, grooming of that tool needs to be done in order to kind of, say, freshen that tool up. You have a similar effect with the P20 or 718 steel, but as you see, it lasts longer before needing that sort of grooming or just kind of quick engineering change. The harder the steel, you don't tend to get that wear, which is why you're able to achieve that much higher tool life with that production tool.
Great. Yeah, there's a lot of information in this table, so you can see the slides after this too to refer back.
Yep. So, want to kind of give you an example of how some customers use our services, use the different design stages or design validation options with the tools. For instance, we've got a medical customer. What they've done is they wanted to go and do a design validation. So they actually invested in a P20 steel. We sampled the parts, ran a small run of parts. They performed their assembly. They did their testing. They found some little issues, some little design tweaks that they wanted to add, not only for part function, but also for assembly. So what they've actually done is they've come back and give us this whole list of changes they want to make. One of it, which is ultrasonic welding. It was a concept that wasn't even on the table when we first had discussions with them. So it was sort of not reinventing, but having to make some decent engineering changes. Instead of going and making all new tools, we actually approach this as kind of a step-by-step or staged approach. So we implemented one change first to see how the customer liked it. We implemented another one and another one until we finally gotten to the point where they're happy with the assembly, which will then, once it's done, allow them to use that tool for production, for beta units, for initial runs. And then their plan is to actually exhaust that tool. And then once they get to that point, invest in the full production tool.
Awesome. Yeah, great example of how to use injection molding throughout the entire development cycle. Now let's talk a little bit more about how to make sure you're getting quality injection molded parts, because quality overall is going to contribute a lot to your timeline as well. You want to make sure you're getting the parts that you need the first time around. So one way you can make sure that you're getting the parts you need is to work with really experienced mold makers. One thing to think about is how many molds does your mold maker produce annually. This will tell you whether they have all of the necessary tools and processes in place, and you'll also get a sense of the resins they might have experience with. You want to make sure that they have the capabilities that you need. Another key thing to think about is whether they have people who are invested in the quality of your parts. So you want dedicated QC at the press, making sure that the parts coming out are going to fulfill your needs. So for an example, Fictive has SQEs at all of the injection molders, making sure that those process parameters are dialed in and you're getting the quality that you need. Speaking of process parameters, that's another big effect on the quality of your parts. So the basic initial process parameters that you put in are going to get your quality to about 80%, maybe just fine for prototype parts, especially if speed is key and you just need some parts in hand to start testing and validating. But then spending a little extra time to take that quality to 95% by dialing in those process parameters more will get you to where you need to be for bridge parts. Maybe you're just about ready to go into production, but you're making some final changes, testing out the production process. And then that little extra time, which overall is a lot of time and contributes to that 8+ weeks lead time for production parts, but that will really help you perfect your process parameters. And again, that's where you want someone there at the press who's dedicated to making sure that those parts are coming out as you need and spending that time to dial in those process parameters. So if we look at how it might look like if you wait to incorporate injection molding until mass production or just before, you might do your initial prototypes with 3D printing, do a few design cycles with that where you update your design, make some more prototypes, update your design again, and then you get final prototypes. You feel like your design is ready. So then you engage your tool maker and start cutting the tool. But at this point, you might find, oh, this part isn't perfectly suited to injection molding. We need to change some thicknesses and some draft angles, but you've already been through all of these design cycles. So you're kind of redoing some changes that maybe you made. However, if you're thinking about injection molding a little bit earlier, you can cut out some of these additional unnecessary prototyping runs. So you start 3D printing your initial design to make sure it's going to look and work okay, and then you start engaging the tool maker, maybe get some DFM feedback and update your design, then make some final prototypes and start cutting the tools. And hopefully by incorporating this earlier in the process, you can validate the injection molding design and process sooner, and you have a greater ability to make more complex designs and hold tight tolerances, and maybe even with a more appropriate material earlier in the process. So one way to think about it is start working with the toolmaker when your design is at 85%. Don't wait until you're all the way there, because you'll save a lot of time and money when you don't have to redo those design changes.
So next on the agenda, we want to explain how you can actually decrease your lead time 5 ways. So using common mold base, I mentioned it earlier, a lot of times with the prototype aluminum tools, you're using a core cavity insert. So those are very typically standard sizes, 5" by 8" inserts, 6" by 9, 10" by 10. They're usually standard sizes. Same thing applies for even steel. So there's kind of off-the-shelf tools that will prevent you from having that 2-week design stage that I mentioned on the high volume production tool. So, using those standard mold bases allows the speed of cutting to be increased. You've got steel that's sitting on a shelf that you can start cutting on immediately, and if the tool maker is accustomed to it, they've already got standard cutters also in their CNC machines to help to speed up that manufacturing process with those bases.
So I mentioned getting DFM feedback on your injection molding design, and the best way to do this is the earlier in the process that you can get this DFM feedback, the better. For example, we have a slide of a thickness analysis here for a part that may be made by fictive, and so you can see right away where there are areas that might be a little too thick, and you might see sink marks. And some other changes that you can make to just make your part more moldable and ensure that you have higher quality parts in the end. And so this higher quality also contributes to the speed of your process overall, because getting the parts that you need at the quality that you need the first time around will save a lot of time in design cycles and reordering and making other changes. So again, contributes to speed and quality. And for this preliminary DFM, you'll want to look at the draft angles, thickness, as we see here, and then weld lines. But there are a lot of other factors that you can look at as well. And this contributes to the continuity and efficiency of your design process too, because when you're getting this DFM feedback at this stage, you know that it's more likely that the same people are still going to be working on this. So the same engineer that's ordering this will be able to incorporate that feedback and make any design changes before passing it off to the next team or the next step in the process. So again, getting that preliminary DFM is really helpful. Getting it with the quote, though, is not that common. And so another way Fictive can help out with any part that you upload for injection molding. You will get DFM with your quote. And so, again, really helpful for speeding up your overall process.
Streamlined communication. Obviously, as everyone knows, the communication is key to success with any project. That communication starts at the very beginning of the project during quote stage, all the way through the end, just providing a tracking number. So we all know without a good communication, any project, even if you've had the best intentions early on, probably has a high likelihood of failure. So having a partner such as Fictive that is the ability to have some streamlined communication, it really is critical. At the same time, having a dedicated contact, having one point of contact that you work with, so you're not being handed off from person A to person B to person C to person D within that company, and that handoff maybe isn't very fluid, maybe is just a little bit clunky. Having that good handoff, you do have it to talk to more than one person at that company is critical. So time zone, obviously time zone is a big one. Having someone that is, I'll call it maybe a 1 or 2 time zones away is also helpful. The one thing that I know a lot of people do is, you could go and find maybe a shop that you want to work with that's in China, for instance. Obviously, knowing that you're going to be working with a shop that is that many, hours ahead or behind, can make things pretty difficult. It now prevents you from, having a nice time at night because you're having to get on the call with the partner that's overseas, at midnight and or early morning. So, having someone to communicate with that is local to you it truly is important and key aspect of just the communication strength.
Number 4, working with highly vetted suppliers. And so this is something I touched on a little bit with making sure you're working with experienced mold makers. But when you go to start injection molding your parts, it can be difficult to actually find an injection molder. How do you find them? How do you start engaging with them? And how do you know that they're going to produce the parts that you need? It can take months to go through this process, and you're still going to experience a lot of risk. How do you know that the quality is guaranteed? So when you are able to work with highly vetted suppliers, then you can meet your lead time and prices without so much risk involved. And they will be capable of handling whatever parts you need. They have that experience from making many molds per year, and they have those processes in place already. And this is a contributor to speed because the biggest thing that will hurt your lead time and your overall process timeline is getting parts that are out of spec. When you get those parts that don't work, you need to make design changes and reorder and maybe wait for tool modifications or a whole new tool, and then again cutting the tool and remaking those parts. So Fictive is very helpful in this case because we have a network of manufacturing partners that we have already vetted. We already have ensured that their parts are high quality and they meet the lead times that you'll need. And we also have a continuous rating system. So every time they complete a project, they are, checked again. And so we only have the best molders and the best suppliers working on your injection molded parts. This is super helpful because, again, you want those high quality parts on time right off the bat. And paying for quality is worth it because in the end, time is money and you don't want to lose that time in your process.
All right. The 5th way to help save money, save time, using a digital manufacturing platform, again, such as Fictive. Using this actually kind of goes back to the previous slide that I talked about, which was communication. Having the ability to upload a part to a platform to provide all of your program or part related information, obviously is the biggest step to be able to give communication to anyone who's going to be touching that project on the back end. Having that easy, streamlined process actually allows for saving time. At the same time, it also allows a continuous partner that you're working with. So you could work with someone on the 3D printing side of things. You can then move into that injection mold side of things that we've been talking about here, or anything else you may need on a project, even if it's something CNC related or cast urethane. So having that that manufacturing platform is critical. The one thing you want to make sure that you're keeping an eye on, though, is that security, that back-end security for your intellectual property, making sure there's some protection and some levels of protection at that partner that you are working with, just to make sure that what you have spent so much time designing isn't getting lost somewhere that you don't want it to go.
Awesome. So we have touched a little bit on fictive and some of what we offer, but our capabilities for injection molding cover both rapid design validation and production molding. So those rapid design molds, we work with steel molds, which, as we talked about, have some higher material availability and finishing capabilities. Sometimes are slower, but because of the processes we have in place and our manufacturing network, you can get T1 samples in as fast as 10 business days. And with that, you can get a low quantity of parts if you need, just to validate a few parts. But you can also go up to 10K units, and the tool life for those molds is actually up to 100K. So very versatile molds there. And then when you move into production, we have you covered there as well with T1 samples in as fast as 15 business days. So still very quick for even these harder steel tools that are great for up to 1 million shots. And so that's a lot of parts that you can make. And again, we have the benefit of also our digital platform, which Kyle just described, really useful for uploading a part and getting a quote and DFM feedback right away. And so if you want to experience that after this, you can sign up for a free account at fictive.com and go upload your injection molded parts. And then just to recap on the key takeaways for today, we talked about both steel and aluminum molds. They both have advantages and disadvantages as tool materials, and the manufacturing location can then be a deciding factor depending on what you need for your project and your application. These are some good things to consider. Also, if you're not already, consider starting injection molding earlier in the process during that design validation phase. Even steel tooling can work really well for this and lead you into bridge production and then full production. You also want to make sure you're using a well-vetted manufacturer who will spend the time to get you the high-quality parts that you need.
Awesome. Well, thank you, Kyle and Kinsey. That was a wonderful presentation. And we're heading into the Q&A portion. So for anyone in attendance, if you'd like to submit your question, please type your questions in the question window on the side of your screen and hit submit. Our first question is, what types of 3D printing technologies are used for prototyping in the manufacturing industries?
Well, I mean, there's lots of options. There's obviously traditional 3D printing. Obviously, there are some people that are really trying to experiment. They've been trying to experiment for years, 3D printing molds, but it's actually, in my opinion, about the same cost sometimes as you would see for a prototype aluminum mold. So there are people that are trying to experiment with 3D printing molds, but there's really no way of getting a true 3D print with the injection mold process. There are two kind of still different processes.
Excellent. Our next question asks, what injection process is offering better compared to use 3D printing methods and additive manufacturing methodologies in general? Could you comment on the pros and cons and why we should keep using injection molding in production?
Tolerance, actually, to me, is going to be the biggest takeaway there. You tend to have, I mean, it's getting better, but you do tend to have a little bit looser tolerances still with the 3D printing or additive manufacturing side of things. With injection molding, because you're using that mold, you have a set size that it can be, and it's repeatable. So you may run 100 3D printed parts, and all could be just off by just a little bit, where you can run 100 injection molded parts and the consistency would be there. And you also get better material properties, maybe not better, but again, the material properties are a little bit different than you would get out of a 3D print.
One other note on this as well for injection molding during production. Again, we talked about the speed of pumping out the parts when you have a mold that can just pump out part after part all day long. That's going to be much more fast and efficient than 3D printing individual parts. Even if you have a lot of machines running at a time, you're not going to be able to get that quantity. So that's another pro for using injection molding during production.
And I think that leads us into the next question is, do you have to make multiple molds at the same time during this time? I think you were just talking about that, Kinsey, like how you can do multiple runs at the same time, correct?
Yeah, that's a good question, and maybe Kyle can touch on this too, but I think it depends on the quantity that you do need, because a single mold, single cavity, as we touched on, you can get 500 to 1,000 parts a day, and maybe that's okay. But then you can also have multi-cavity tools, which can get even more parts. And then if you really need a lot, then yeah, you can have multiple molds, multiple presses running.
Yeah, actually, I was watching when this question came in. This was during the customer example that I gave, where we talked about engineering changes. So actually, no, in the case of that customer story, it was actually the same mold. We just performed engineering changes to that mold, where we can make design changes to the same mold and not have to make a whole new tool. So it all uses the same mold. Again, usually if you start having a demand that exceeds what you're requiring, that's when you start looking into those. Maybe it's a second mold, or you start looking at a multi-cavity mold at that point. You also have an option where you can have a mold base that's big enough to accommodate multiple designs. Maybe you start with a single cavity, and then once the need comes up for more parts, you can then, in theory, add cavities to that same mold down the road.
I think this leads to a nice question here about, average size. What is the average size of an injection mold? What is the thickness of those molds? What can you expect from a typical injection molded part?
It's a huge range. You'll have some people that build very small little micro molded parts, all the way into car bumper size parts. So I would say on average, palm of your hand is usually what I kind of say. But for us, we actually had the ability to go up to a roughly 2,000 ton press, and a 2,000 ton press can make maybe not quite a car bumper, but can definitely make some bigger panels that you would see in the car. You mentioned thickness. Thickness is a little bit, depends a little bit on the material. I always kind of gave a rule of thumb that, in inches, I kind of like to see a part that's between 30 thousandths of an inch up to maybe 140 to 150 thousandths of an inch. There are some fillers that you can put into material to help give you thicker walls. But on average, I like to stay with that 30 to, again, 150 thousandths of an inch thickness.
Great. Our next question reads, how does fiberglass filler increase press mold wear?
It definitely is a contributing factor to that wear, because the way that whether if it's fiber or glass, there's injecting into that tool. It's running along that tool surface. So where it hits, you're creating a little bit more wear, especially at that point of the gate, where the plastic is actually being injected into that mold. That's where you start seeing a little bit more typically of where the impact of fiber or filler in general can actually impact the tool wear, which is usually why what you see in the industry is what you would get out of the same mold, same design out of, say, an ABS material, you get 10,000 or 50,000, but you start adding glass, it kind of knocks that tool life down, sometimes in half or more.
Our next question is, what percentage of overall size can be changed or modified in process details?
I'm assuming by process details, meaning at the press and what you can control. You have limited access, you have limited control, I should say. You can get some variance. So, again, a lot of that's going to depend on the overall size. If you have a great big part and you have some maybe poor processing, you can get some differences. In the tool itself, it's kind of the same because you fill the tool. It's usually after, when you start, when the part's ejected and it's cooling, that's when you start seeing the size come into play or the size difference come into play.
Great. The next question reads, if you need to produce less than 1,000 parts, what would you recommend between injection molding, urethane, or 3D printing?
The rule of thumb, and again, it's a hard question to answer because the part geometry has a lot to do with it. If it's again, I'll just give it the palm of your hand. If you're needing, I've always said, maybe 10 to 25, 3D printing to me has always been a great way of doing that. When you need in that, say, 50 to 100 parts, cast urethane is actually a great way of doing that because, those cast urethane or silicone molds can usually last between 50 parts, 25 to 50, but silicone molds are easy. So usually to me, when you get above that 100 to maybe 200 range, that's typically where I've seen that the cost savings of injection mold helps. And to Kinsey's earlier point, the consistency, you're going to get a lot better consistency on 200 parts than you would, 200 3D printed parts or 200 urethane parts.
Great. So our next question reads, what is the difference between bridge parts and production parts?
Really nothing. You're making a mold, you're using the same material. Another example of what we're doing right now for our customers, we're actually taking a production mold that they've already started and we're building that design validation or bridge tool. And they actually provided us where they're injecting the parts, so their gate location, as well as their ejection plan. And so we're actually mimicking the same plan that they're taking for their production on their bridge tool, their low volume tool. So really everything should be the same, all said and done.
Our next question reads, which draft angle is the priority?
Not sure I 100% understand the question. Obviously, draft is critical in getting the part to remove from the tool. We tend to not require lots and lots of draft. We can get away with a half degree of draft on all surfaces, between the core and the cavity and the ejection, and actions rather, I apologize. But I'm not sure if that answers the question or not.
You can always follow up with them later if need be. So I think there's a good question here that discusses adding cavities, and it's just a good question about how far along the process or anywhere in the process can you make adjustments. So the question reads, is it feasible to add cavities to an existing mold if the tool maker is aware of this requirement at the start of the project? And I think in general, are you allowed as an engineer, as a designer, to make adjustments to the mold throughout any part in the process?
Yeah, it actually kind of goes back to one of those 5 points, the communication. Having that knowledge up front, it certainly should allow you to do that. There are companies that don't want to do that because they are, I'm not going to say set in their ways, but they have a certain process. You have you want to make sure you work with someone that can kind of, I say, ebb and flow with what you need. So to answer that question, yes, having that communication early to know that, I want to start with the one cavity, but I want to add 3 more once I've proved the design out. It should absolutely be done. Having it done early on is, again, critical because of your gating strategy to make sure that you're allowing enough room in that tool. So you may need to go to a slightly larger mold base than you had accounted for the single design, but having the ability to then add cavities 2, 3, and 4 is what you're looking for there.
Excellent. Our next question is, what defects can mainly occur in the injection molding process?
Kenzie, you want to take that one?
Yeah, I can talk to this one a little bit. So a big one is sink that we mentioned on that slide with the thickness analysis. When you have parts that are maybe too thick or they don't have as good flow of the material to that part, maybe the cooling isn't as even, you'll end up with sink marks, which are common defects. You can also see warping, I think, again, with the thickness of the part. So there were some questions about thickness too. You always want to make sure that you have an even, uniform thickness, or at least gradual changes in the thickness so that you have a good uniform flow throughout the part and you don't see as many of these defects. Any other thoughts, Kyle?
Yeah, I mean, there's other issues, more maybe like warp. Again, part geometry has a lot to do with how much the part will warp. Communication early on to predict the warp, and some softwares can simulate and give you a prediction on warp, but I think that'd be the other aspect of it there.
Excellent. So our next question is the platform able to estimate cycle time? And I think that might be just a good question for any process. Do you have, how much information in terms of how long it will take is given to the engineer or to the designer?
Kenzie, you or me?
I can take this one. Yeah, so platform, I think they mean the fictive platform. And this slide that's being shown here is an example of our platform. So when you upload a part for an injection molding process, for instance, you'll have your 3D model in step format as shown here. And so that's going to provide the geometry information, but then you also choose, the number of parts you need, any secondary processes, what material you're using. And so all of this information goes into our platform, and then you'll get a lead time estimate. And so the basic answer is yes, we can estimate that lead time and tell you how long it's going to take to get your T1 parts for injection molding. And you can play around with that a little bit too. If you need it faster, it may cost a little bit more, or if cost is an issue, then you can also choose or opt for slightly longer lead time. Similarly, our platform can handle 3D printing or CNC machining parts, and we can estimate the lead time for those as well. So, yeah, hopefully that answered the question.
Thank you. Our next question is, what's an example of material that you cannot mold with aluminum?
A lot of high heat materials, for a couple of reasons. Obviously, a lot of times when you have a molder that doesn't necessarily run a lot of steel molds, they have presses that are more accommodated to those materials that can run aluminum. So your high heat materials, your engineering grades like Ultem or polysulfone or LCP, those real high heat required materials, aluminum tools can't maintain the temperatures needed to mold in that. So, for instance, aluminum can usually withstand, call it 275 F, where the mold processing required for Ultem is usually starting at 275. So you don't have the variance that's required to dial in that processing for, again, those high heat materials. with aluminum. Sometimes you get into just overall tool life. So you can mold, say, a real high glass material, but you may only get 30 parts, 50 parts, 100 parts before that tool is already creating parts that are out of spec, just because of that wear that occurs so quickly with aluminum. So again, a lot of the high glass or high filled materials, it's more difficult to run on aluminum.
We have a question here about surface finishes. What is the best surface finish for ejecting low no draft parts? Is it a highly polished or less polished to improve air entry?
It's not necessarily a textured finish, but it's sort of, again, if I go on the SPI standard, it would follow the C3 or in the C range. Reason why is because of surface. It's the surface that's actually touching the tool. So you have some variance there. So with a high polish, you have more surface finish that's actually applied to the tool of the part transition to the tool, which creates a bit more of a struggle to eject the part. So usually within that C, maybe call it B3 to C3 range would be better for those no draft finishes. Obviously without draft, you do still have some cosmetic imperfections, so you may have some drag marks, but as long as this is understood and acceptable, it can be done. Excellent.
We have a question here, and I'm not familiar with the term, Kyle and Kinsey, so I'm going to leave it up to you guys. What is the TAT difference between urethane versus injection molding? Maybe we could, if you guys know what TAT is?
I actually don't know if I've ever heard that term before.
Neither have I. But maybe we can discuss what is the difference between a urethane part versus just an injection molding part in general terms.
Urethanes are thermoset materials, so you have a two-part materials that are mixed together. So an A and a B cured together. Once those are mixed together, you then have material properties that are similar to, call it an ABS or polycarbonate or something along those lines. So again, it's an engineered material versus, say, a thermoplastic, which is injection molding, and it's in a pellet form. It's molded, and when it cools, it reforms that same material property that it started at in that pellet form.
Okay, we got some clarification from the attendee. TAT is turnaround time. So I guess is there a difference in turnaround time between a urethane part versus an injection molded part?
Urethanes tend to be a little bit slower process because it is a room temperature cured process. So you're sometimes only able to cast 2-3 parts a day, where you also still have to create, if you do it the traditional way, a master pattern, you then make your tool. So sometimes it takes 2 weeks just to get a first article part out of a urethane tool. And you're looking at basically the same turnaround time for injection molding. The only difference is once the tools are made, you're then able to run, as Kinsey mentioned earlier, 500 parts a day out of an injection mold tool versus 2 to 3 parts a day out of a urethane tool.
Excellent. We have a question here about prototyping and upscaling a mold. After prototyping the part by 3D printing a single or two cavity mold, what is the best practice when thinking of scaling up to an 8 or 16 cavity production tool?
Man, that's a good one. I think that kind of falls into that design validation, really. That's kind of what we've been talking about is, you get your 3D print, you determine, you then go into that single cavity or maybe it is a 2 cavity. I'm a big advocate for, if you know that the demand is going to need and require an 8 or 16 cavity mold, you can start engaging that, that tool maker at that point, or you use that single cavity, 2-cavity tool, and you run it as long as you can. You run it for 25,000, 50,000 parts, and then at that point, you've maybe had some learning opportunities. You've had some, oh, I didn't think about this, after you've been using it for 6 months, and you can make your design changes before launching into that full production, 8-cavity or 16-cavity tool.
Great. So we have a couple more questions before we end the hour here. And this is a question, I believe, about fictive processes. What materials can you use for injection molding?
Kinsey?
Yeah, so we basically all like engineering materials, most plastic resins, we're going to be able to inject for you. We have full list on our website, but we can source other custom materials if necessary and definitely work with you on that. So not too many limitations there other than maybe for the tool and what the tool can handle, but pretty wide range of possibilities.
Excellent. And then our last question here is, can you review a hot sprue and what benefit that may provide?
Ooh, I don't know if we have that kind of time, I'll be honest. A lot of times what, the quick answer is a hot runner or a hot sprue. It actually helps to improve and increase your cycle time. It also helps to minimize scrap. So you don't tend to have as much waste when you're using that type of a tool than you would with a cold running tool.
Excellent. Well, Kyle, Kinsey, thank you so much for your time. This was a wonderful presentation. Thank you for bringing your expertise to this topic. Again, for anyone in attendance, if we did not get to your question, you may receive an email response later on from the Fictive team answering your particular question. To learn more about Fictive and to get an instant quote for your injection molding needs, please visit fictive.com. That is fictiv.com. And if you missed any part of this presentation, it will be archived shortly, so you can view it again, refer someone to it, or access the related materials. For everyone in attendance, have a great afternoon, and I believe we have one poll question at the end of the presentation. Is that correct?
Nope, I think we did that earlier.
Oh, I apologize. Well, thank you again so much, everyone, and thank you for attending. Thank you for Kyle and Kinsey, and thank you to Fictive. Everyone, please have a great remainder of the day.